Yeah, good afternoon. Thank you for coming back. Yeah. Last time, we were discussing the entropy of a source. And by a source, we just mean a random variable, which takes some a values from some alphabet with corresponding probabilities. And we defined, somehow, we came to the conclusion that this quantity, the entropy of X, is important for certain engineering purposes. And this quantity was defined as you take the elements and so maybe a slight difference in the notation here and here. So for each element X, P subscript X is its probability. Yeah. So, and this quantity played a role in two theorems that we wrote. So one of them was that so you have this source and you would like to assign code words of zeros and ones to these symbols of your alphabet, and you will count the expected cost of transmission, which is the expected length of a code word assigned to a symbol from here, when the expectation is taken over with respect to this probability distribution. Now, although I described transmission as involving two parties, Alice and Bob, it is, of course, a more general thing. When you take some information, outcomes of your experiments, and you record them and put them in the disk, and then you read the disk many years later, you can regard that as a transmission from yourself to yourself. Okay. So what we here talked about transmission cost actually is about how well you can compress your message, so that so you use the least amount of disk space. So the second theorem tried to get rid of this plus one and try to get an exact characterization of some aspects of this source in terms of the entropy function. Okay. So let me write that down. So And what was this T delta n? So we imagine that we draw from this source independently n times. So our samples all land in this set, which is, and in this set, we try to identify a set A delta, yeah, which captures 1 minus delta of all probability. Or it doesn't matter if it is delta or 1 minus delta, but yeah, psychologically it feels better if it's 1 minus delta. So a good fraction of the probability. And we ask, yeah, so this quantity is the minimum over all such sets A delta, such that the probability of A delta is at least 1 minus delta of which quantity? Log of cardinality, and we take so, and I just stated this theorem without probably explaining carefully where this arrives, how this comes about. So my plan for today is to slightly think about this in a deeper fashion, and then move on to conditional probability. And the analysis that we will do to better understand this will be useful in whatever we do later. So suppose we draw from this source n times, and we get some symbols. Let me call them Z1, Z2, Zn. Each of these Zi's is one of these. Now, this Z bar is the sequence which has been obtained by drawing from that source independently n times. So it lands up somewhere. Now the question is, what do we expect this Z1 to Zn to look like? Yeah, you had this source, K is some small number. In the case of a coin toss, K is 2. Yeah, if you roll a die, 6. Yeah, whereas this number n is some large number, we at some point might even be tempted to take it to infinity. Okay, so it's a very large number. But if you draw independently from a source n times, out of these Zi's, some of them are going to be x1. Some of them are going to be x3. Yeah. What do you expect in a typical situation? The number of So this is the number of occurrences of the letter A in X bar. So how many of these Zi's are A? Yeah. So this quantity, what do you expect it to be? Yeah. Yeah. So let us define a sequence. We say that X bar is epsilon typical if the number of occurrences of A in X bar so you look at this sequence, suppose A was this, and this number was 1/3. Then you would expect 1/3 of these symbols to be A. If it is 1/3 plus or minus epsilon, we are happy. If it is deviates from 1/3 by more than epsilon, then we will not call this sequence typical. Okay, so we will say that X bar is typical if this quantity is true for every A we cannot expect it to be exactly PA. There will be some deviation, but all deviations are within control. Okay, yeah. Now, here's the claim. Yeah, so let me set a value for epsilon now. So let me set epsilon n to be, yeah. So let's say, okay. Yeah. I'll see, yeah. But it's a pretty small number, yeah. And the claim is yeah. So please don't take these numbers 110 and n to the 2/3 very seriously. You could have put different numbers, but the point is that almost all sequences, once you make n large, this probability is going to 1. Yeah, that means if you look at this set and ask which are the typical sequences and compute their probabilities, their total probability will be almost 1. Okay. This n, yeah. So this n is the number of occurrences of the letter A in X bar. Okay. So we expect it to be about PA times n. So I've divided by n. So NA divided by n, NA divided by n should be about PA. Yeah. And so maybe I should have used a different language. So if you look at this vector, yeah, so you take these number of occurrences. Sorry, why did I write X bar? Sorry about that. Yeah, so this, by Xn, I mean you have sampled from this source n times, and then you get a long sequence, and that sequence is epsilon typical most of the time. Yeah, sorry, I didn't finish this sentence. You should think of this as the empirical distribution. You had an actual source, it has its characteristics, the probabilities. You drew a sample from that, and in the sample, you saw what were the various probabilities, proportions, the frequencies of these things, and that is the empirical distribution. And we call a sequence epsilon typical if the empirical distribution doesn't differ from the actual distribution by more than epsilon in any coordinate. And the claim is that most sequences are epsilon typical, where epsilon is a number like this. Okay. Now, what does that mean? I'm just drawing the same picture again. Most of the sequences are epsilon typical. Yeah. Now, what is the probability? Yeah. So if Z bar is epsilon typical, then what is the probability that so if you look at any such sequence Z1 to Zn, what is its probability? Yeah. Well, you should ask how many times A appears in it, and suppose A appears 5 times. Then you will write what? P subscript A to the power 5. And B appears 7 times, P subscript B to the power. So this probability is product. Yeah. A belonging to X, P subscript A. What should I write here? N of. Yeah. Now, if your sequence is actually epsilon typical, then what do we know about these numbers? These numbers are pretty close to PA times N. Yeah. So I'm not going to bother about these slight error term of epsilon. Yeah, I might write it in the notes, but let us do a crude calculation. Maybe if there is time, we will make it better. So let me just apologize for what I'm doing by putting approximate here. And so this looks like 2 to the power. I'm going to take a log. What should I write here? The product will become sum, and yeah, that is our familiar formula for entropy. So what is the message? That if you take a source and take IID samples n times, then most of the probability is sitting on Z bars whose individual probability looks like 2 to the power minus n times entropy of X. Yeah. So now if anybody wants to encode some sequences out of this, but is willing to ignore some of them, yeah, but still they want to do well. They want to get 1 minus delta. Now, the typical sequences are almost everything. So basically, they have to focus on the typical sequences, because even if they collect all the non-typical sequences and give them nice code words, they will only capture this much of the probability. They would like to capture a good fraction of the probability. Now, if you want to capture a good fraction of the probability, you will have to catch these typical sequences and provide them code words. Yeah. How many typical sequences do you need to gather a probability of 1 minus delta? Well, each single typical sequence gives you only this much probability. Yeah. So you go pick this one, then you pick this one, pick this one, pick this one, and you pick these so that it becomes 1 minus delta. But each of them is only giving you this much. So any attempt to capture this much probability would involve how many sequences? The cardinality of A delta has to be at least yeah, with the usual approximate signs. Though they are all lower order terms here. Okay, yeah. So trust me on that. So this starts looking like 1 minus delta 2 to the power n times so now you see that any attempt to capture 1 minus delta, this set will start looking like 2 to the power n times entropy times 1 minus delta. When you take a log of this, you will be left with n times h of x, and then log of 1 minus delta, plus log of 1 minus delta. But then you are dividing by n, and then taking n to infinity. This log of 1 minus delta, if you divide by n, that's going to go to 0. Basically, you will be left with n times entropy. Okay. That is the reason why this quantity will be at least h of x. On the other hand, suppose I picked up all the epsilon typical sequences, all of them. How many epsilon typical sequences are there anyway? Each of them has probability this. Yeah, has probability at least this. Last time I said at most this, now it is at least this because this number was very close in either direction from PA. Yeah. So the number of typical sequences maybe I should say. You cannot have that more than that many typical sequences because each sequence has substantial probability. Yeah. Which means if we now gather all of them into this, into our set A, then we will get a probability which is this, which is anyway much more than 1 minus delta. Okay. So which means that if you allow yourself this much, yeah, a set of this size, then you would have captured all the probability. Yeah. So let us just interpret what this means. So you're performing this experiment again and again in your lab, and you have a collaborator who is far away, and you want to send the results of your experiment to the collaborator. Okay? And your professor says that, per experiment, I'm going to allow you R uses of the channel. You can send, on average, per experiment, R bits, R for rate. So the budget, or let me put it as B, yeah. So you keep performing, you perform a long experiment, many experiments, and now you're trying to send the result to your collaborator on the other side. And your budget is, you want to use only B bits per experiment. Yeah. Now, if B is less than h of x, yeah, that means then to encode the result of n experiments, you are using only 2 to the power n times b, different strings. That means of the typical sequences, you would have been able to pick only 2 to the power n times b sequences and provide them code words. But then, if this b is much less than the set of typical sequences, then you will only succeed with vanishing probability. Okay? That means if you are trying to come in your language, at h of x, there is a phase transition. Yeah? Okay? That is the message of this theorem. I was struggling yesterday to be a physicist. Yeah? So, what is the meaning of the first theorem of Shannon? That if you're trying to communicate with a budget of B, yeah, if you try to do any compression of n experiments into B bits, yeah, B bits, B times n bits, B bits per experiment, if B is less than entropy, almost all the time, what you have seen on this side and what Bob thinks you have seen on that side will be completely wrong. Okay. But the moment you are allowed a budget beyond entropy, you're happy. Yeah, almost all the time, the outcome of your experiment will be faithfully decoded. Okay, does this make things better? Thank you. Good. So that's all I wanted to say as a clarification to our theorems from last time. And given such a picture, you might feel that, okay, yeah, we should think of h of x as the amount of information in the source, because once we are below this h of x, we have no hope of transmitting the information. And the moment we cross this, we are able to transmit information with high probability. Yeah. With probability of error which vanishes. This is the probability of error. Most of the time, we will succeed. Question?
Last time you said like when there is continuous distribution of energy,
yes,
the entropy becomes negative.
Yes.
So if I will,
yeah, so that is differential entropy. So yeah, so don't think about continuous. Okay. Yeah, so that continuous entropy has its uses in communication theory, but things become a little, I mean, one needs to do things carefully. We will say discrete. Yeah. Questions? Yeah. Yeah, so yeah, I'm not sure of that. Also, so what we say is, so what are we plotting here? Yeah. So if we plot the probability of error as n goes to infinity, what we know is actually it is 0 here. And at this point, it is the moment you are even slightest above entropy, by choosing a long enough block length, you can drive the error down to 0 or the probability of success up to 1. But if I'm exactly at h of x, your professor says use h of x, not 1 decimal extra. Okay, then what is your probability of success? Now, this has been studied, and there are sources where it is 0. Depending on your source, it can be here, it can be here, it can be here. Yeah. So the behavior at h of x is not known. Is not always the same for all sources. But below h of x, the function is 0. Above h of x, this is 1. Now, you are saying, what about, yeah, so most probably it will be like h of x plus 1 over square root n or some scaling of square root n. Yeah, because that is what controls the large deviation results that go into this. Okay. So far, when we are discussing entropy, we have been discussing the entropy of a single random variable x. And sometimes when we think about multiple random variables, they were all random variables which were, when I write xn here, xn is several copies of x, but those x's were all drawn independently. Yeah. But that's not how life works. We have random variables which are not independent. So we consider the situation x and y. X and Y is a pair of random variables. So it has, say, it takes values in a set X cross Y. Yeah? And so it is determined by so I will have to specify these many numbers to tell you what is the probability that X takes the value little x and Y takes the value little y. So this is also a source, but it just happens to have two components in our mind. Okay? And there is an entropy. And this entropy is the same thing. Over all choices of xy in pxy log 1 over. Now, when you have such a pair of random variables, x alone is also a random variable, and it has its own marginal distribution. Yeah, and we can write about. So this is the entropy of X. Now, when dealing with random variables, which are not independent in probability, we are taught to think in terms of the marginal distribution. And there is one more word we are taught, conditional distribution. That is, yeah. So there is a probability that capital X takes the value little x, and we tend to write this quantity as probability that X takes the value little x times Y takes the value little y. So maybe inspired by that, we can ask, okay, there were these two random variables which Alice observed in her lab. She has just told us about X. How much entropy remains in Y? Yeah. So suppose this was one of those experiments where when X takes the value 5, Y takes the value 6. When X takes the value 7, Y takes the value 8. Y is always X plus 1. Okay? And now somebody told you X. How much entropy remains in Y? 0. Because once you know X, there is nothing left in Y. Y becomes determined. Okay? On the other hand, if you look at the entropy of Y alone, it is the same as the entropy of X, because it is varying with the same distribution, only the numbers, when this is 5, that is 6, when this is 6, that is 7, etc. But one can ask about a general situation where after you are told X, how much information is there in Y? And we define conditional entropy. This kind of cheating here, in the sense, sort of a lazy definition. So there is information in XY. This is the information in X. How much more information is there in XY than in X? And that quantity we call the conditional entropy of Y given X. There is a slight difference between this and probability. When we do conditional probability, we do conditional probability of something given X equals little x. We are just writing X. We are not saying conditional entropy of Y given X equals little x. Okay? Yeah. So this is the conditional entropy of Y given X. Okay? Now, the first scary thing is this quantity always non-negative? Could this be negative? I mean, there is a negative sign here. And could it be, yeah, that the conditional entropy of xy is actually less than the conditional entropy of x? Okay. So we need to do a small calculation to reassure ourselves. So let us write it down. So what is this conditional entropy? What is this entropy? Summation over xy. I'm not writing the ranges. Pxy log of 1 over pxy minus summation px log of Is that clear? Sorry, my font is not very good. I mean, this is supposed to be small x, yeah, and this is capital X. All right. Okay, so still there is a negative sign, which is still a little alarming. But probably doing multiple steps. You understand? This is equal to this. Why? Because I can write this pxy as px times p of y given x. So there is a px here. So I start clubbing things up. And this pxy also, I could write it as px times py given x. And then there is a log that will cancel with this log 1 over px. And all that will remain is log 1 over py given x. Is everybody okay with this? No. Should I do it in 2 steps? I'll just wait. Okay. Yeah, is it okay? So this quantity is exactly this. Okay, very good. Now somehow the minus sign has gone away. And all these quantities are, yeah, non-negative at least, yeah. So is that okay? But there is more to this. This particular expression, this looks like an average taken over x of some quantities which also look like entropies. Yeah. So actually, the conditional entropy is actually an average of various entropies of conditional distribution. So let me explain. Whenever you have two random variables x and y, there is a way to draw a picture for the two random variables. The value x can take various values, as many values as there are elements in the set. X can take those values. What's the probability of taking this branch corresponding to A? PA. Yeah. Now, once X has taken a particular value, Y takes various values according to the distribution P. Y takes various values according to this. Now, if I focus on these numbers here, they are an honest to God distribution on the range of Y. They have that little distribution, and let me call that H of Y sub A. Now, what is H of Y sub A? The conditional random variable Y, when X has already been known to take the value A. So there is a little entropy here. For some other values of A, there is this. So for each occurrence, each outcome, each realization of the random variable X, there is a conditional distribution which has its own entropy. And what is our definition of conditional entropy of y given x? You take the average of these little entropies that you get, but average with respect to which distribution? The distribution of x. Okay. So we have sort of seen two definitions of conditional entropy. One is this lazy definition, whatever remains in xy after subtracting the entropy of x. Okay. But that quantity is precisely equal to this thing. All right. Is that clear? Yeah. Okay. So that's the definition of conditional entropy. And we have discovered that conditional entropy is always greater than or equal to 0 because it is an average of objects which are greater than or equal to 0. Okay. So this obvious thing that, conditional entropy, the system as a whole must have more entropy than a part. The part of the system, sorry, what did I say? Yeah, so the conditional entropy is greater than or equal to 0. So, which means, so since this quantity is greater than or equal to 0, this quantity is greater than or equal to 0, that means h of xy is greater than, if this is greater than or equal to 0, h of xy is greater than or equal to h of x. Okay. Yeah. Which we might think is an obvious thing. Yeah. The amount of information, if somebody tells us x and y both, is obviously more information than telling us only about x. Okay. And actually, much hangs on this inequality. So when I was asked almost 1.5 years ago to talk about entropy, I asked like, okay, so should we talk about quantum? And the organizers forbade me from talking about quantum. But this inequality fails in quantum. And this whole half my colleagues make their living because this inequality fails. Okay. Yeah. When the system is entangled, the part of the system, sometimes has more entropy than the system as a whole. Okay. Now, we thought this was an obvious statement. Yeah. And when obvious things don't happen, we call it quantum. Yeah. All right. So this was one thing. Okay. So we are reassured at least that conditional entropy is the other thing. Yeah, I still have some space. Yeah. I mean, just to defy the organizers. So if you consider this part as x and this part as y, so we are in this state. I mean, you call it an EPR state or something like that. Yeah. So the entropy of this, so there is a way to define quantum entropy, which I know many of you already work on. The entropy of this is 0 because it is a pure state. Yeah. The entropy of xy is 0. But if I trace out the second component and concentrate only on x, if I concentrate only on x, then it just looks like a coin toss with probability half of being 0 and half of being 1. And then its entropy is 1. Yeah, it depends on your log. Yeah. So, so you see, the full system had entropy 0. The part had entropy 1. Okay. Good. Yeah. Don't tell anybody I said this. Okay. Good. Yeah. All right. The other thing is we would think that the entropy of y given x So, understand? I mean, don't look at formulas. This is the amount of information that I get on learning about Y when I already knew about X. And this is the amount of information I would have got if nobody told me about X, but only told me Y. Okay? Now you would think that if somebody told me, if I already had the information about X, Y can only give me additional information. It could be that X already determined Y, in which case I'm not even going to listen to that fellow because I know what he's going to say. Okay? So this looks like an obvious inequality, which ought to be true if our intuition about information is correct. Now, it is true, okay, yeah. And, but it needs a little proof, yeah. So if you rewrite this, yeah, so this is equivalent to this is what we want to prove. This, to prove this is the same thing as proving this. And if I expand this, yeah, using the definition, okay, h of x plus h of y minus h of xy, because this was h of xy minus h of x. Now, so we are claiming this is always greater than or equal to 0 for any pair of random variables, whatever their correlation. Yeah? And this has a name, and it is called mutual information. Yeah? And it's usually denoted by x, y. There are various symbols put here. I'm going to put a colon. Yeah? Just rewriting what I wrote. Excuse me. Just change nothing. I mean, just have given the left-hand side here a name. Yeah. The question is this greater than or equal to 0? Yeah. So, yeah, let's do the calculation. So the left-hand side, or the left-hand side of this is summation over x, px log 1 over px plus summation over y, py log 1 over py minus summation over xy, pxy So tell me if you agree with this. Yeah. So the only difference is instead of px, I have written pxy, but I have summed over y. Yeah. So this part is the same. If I split this as px and sum over y of the conditional probability of y given x, that number would be 1. So basically I have multiplied this by 1, this by 1, and expanded. Okay. So I mean, the main, the reason for doing this is I get pxy everywhere now, and I can write this as summation over xy, pxy log of pxy divided by is everybody okay? No. Sorry, this is just algebra, yeah. the Px is here, the Py is here, and because of this negative sign, the Pxy is in the numerator. Yes? Yeah. And we want to show that that quantity is greater than or equal to 0. We actually saw something like this last time. Yeah. And so suppose P and Q are distributions on some set capital X. Then, if you look at this quantity, this is called Gibbs inequality. And yeah. Okay, so why is this true? Yeah, so somehow it's easier to, so equivalent to summation Px log of Px by Qx. So yeah, I just multiplied both sides by -1 and changed the sign. Yeah. So this inequality, if I prove this inequality, it's the same as proving this inequality. Yeah. And now if you look at the left-hand side, log is a, yeah, we did this last time. Yeah. Log is a concave function. So the left-hand side, yeah. What happened? Am I messing up again? We have proved this. Yeah. So that is Gibbs inequality. And I cannot like overstate its importance. Almost every inequality that we will prove in information theory just follows from this. Okay. So let me demonstrate. So yeah, I'm sorry, there are two statements at two ends of the board which sort of look like the same. So Pxy is a distribution. Yeah, so this is P. Px times Py is a Is that okay? Yeah. So by Gibbs inequality, this relative entropy is always, sorry, mutual information is always greater than or equal to 0. Okay. And by some miracle, this statement, yeah, the mutual information greater than or equal to 0, yeah, is true even in quantum. Okay. So there is this quantity between two distributions, the left-hand side of Gibbs inequality, is called the relative entropy between the distribution P and Q. Or in machine learning literature, or in statistics, it is called the KL divergence, Kullback-Leibler divergence between distribution P and Q. And you can define relative entropy for quantum systems, yeah? And the relative entropy is always greater than or equal to 0. Good. Okay, so questions? All right, so we have described conditional entropy. We know that conditional entropy is not going to be negative. And we also know that the conditional entropy is never going to exceed the entropy itself. The quantity conditional entropy has an important role in the problem of information transmission. A slightly different version of the problem. And I'm going to now tell you this new version of the problem of information transmission between two parties A and B. And then we will see, yeah, how mutual information comes into the picture. That is the main goal for today. What's a channel? So channel has an input alphabet so this is the input alphabet. So you feed a letter from the set X into the channel, and it comes out, yeah, as a little symbol Y from this capital Y. But when you feed a little x, it doesn't always come out as the same symbol. This channel is probabilistic. Yeah, when you feed something, it might send various things. Okay, so it is described by this matrix. Yeah. So you have to tell me, if you tell me that you have fed the symbol A, I will tell you the probabilities of obtaining the various letters B on the output side. Okay. Now, let me give you some examples. This is a channel where the input alphabet and the output alphabet are both 0, 1. Yeah? So it's a channel into which you feed 0 or 1, and what comes out is also 0 or 1. But binary symmetric channel with error epsilon. So when you feed it a 0, or you might feed it a 1, but if you feed it a 0, 0 comes out with probability 1 minus epsilon, but it might send you a 1 with probability. And if you feed it a 1, it but it might send you a 0 with probability epsilon. Okay. So this is a particular, yeah, it has a non. So the input alphabet, X is 0, 1, and Y is 0, 1, and star. Okay, so it can be 0, star, or 1. So if you feed it a 0, most of the time it will come out as 0. But with a certain probability, what you are sending will get erased. Yeah, but thankfully, they will put a star there saying that we don't know what it is. Okay. And if you feed it a 1, so this is a channel. This is a channel. Depending on the way your communication has been engineered, it will have its own characteristics, input set of symbols, output set of symbols, and the conditional probabilities of receiving a particular output symbol when an input symbol is fed. So the problem is the same. Alice now has a long string of zeros and ones. And she wants to transmit this to Bob. So this is what is being streamed in your lab, and you want to tell your collaborator about this. Okay. And I mean, your stingy advisor didn't buy the best channel. Yeah. He bought this. Yeah. So it makes an error with probability epsilon. So what will you do? Yeah. So this is the channel. Yeah. Let's call it C. So you would like to send these symbols through this channel, and you would like the other person to get the answer right. So one thing one could do is each letter here, say, send it 3 times. Yeah, you send it 3 times. And what do you ask? What does this person on the other side do? Suppose they receive, they have to guess what you really meant to send. You could have sent 0, 0, 0 or 1, 1, 1, but they received 0, 1, 0. They could perhaps say, okay, I'm going to go with 0. Yeah. And what would happen to the probability? Well, the probability that you send 0, 0, 0 and there are 2 errors will go as epsilon squared. Yeah, maybe 3 epsilon squared or something like that. So the probability of error goes from epsilon to epsilon squared. And if you want to drive down the probability even further, you could imagine that each letter here you could encode into a large number of bits, and you could ask the person on the other side that, you know, if they're all the same, of course, most probably things are okay. But if things go, you know, if you see both zeros and ones, just go by the majority. Okay. So that will drive down the error, but what is happening to your rate? For each symbol that you are transmitting, each little outcome of your experiment that you're transmitting, now you have to send 3. Yeah. For every 3 uses of the channel, you're able to send only 1 bit of information. Okay. And if you want this error to be down, you one of the gems of combinatorial analysis. So I hope I succeed in conveying it to you properly. So the idea is we should Alice decides that she will wait for n experiments, and these n experiments will result in n outcomes. Actually, yeah, so maybe I should not use the word. Let me explain. So she's going to use n, the channel n times, yeah? So these are, think of R as a small number, like 0.9, yeah? So she's going to look at 0.9 n bits here and somehow expand them to n bits by adding some redundancy, okay? And these n bits will be passed through the channel, okay? If the channel has different alphabet sizes, some other way of encoding will be done. But the point is that this is the raw data. This raw data will now be encoded into something of a certain size, and then that will be fed to the channel. It will come out as a block of symbols, but what was transmitted here may or may not agree with this, because this channel independently behaves according to its characteristics. Looking at this, the person on this side has to determine what was intended, okay? And the ratio between this length and this length, between this length and this length, is what we care about. Because if you take R times n bits here and encode them as n bits, yeah, your rate of communication, yeah, per channel use, you are sending R bits. Yeah? You use the channel n times, but sent only Rn. So per channel use, you sent R bits. And what is the maximum R that you can achieve? You saw that there was a phase transition. If you did, yeah, if you tried to compress to less than entropy, you definitely made huge amounts of error. The moment you allowed yourself a budget of more than entropy, you could almost go errorless. There will be a similar phenomenon here. Below a certain value, yeah, I have not said it will come out of mutual information. If you keep your rate of transmission below that, then you will succeed. Yeah. So there will be, we will define something called a capacity of a channel. Yeah. So it's all coming. Yeah. Something called a capacity of a channel. If your rate of transmission is below the capacity, very good. You will be able to communicate with probability of success close to 1. The moment you cross capacity, yeah, you try to stuff in more information from the stream into fewer users of the channel, you will almost always make errors. Okay. Again, there is a sharp threshold. Okay. And that will be Shannon's second theorem. But let me motivate and see. Yeah, we have time, don't worry. Sorry, I have not written anything down carefully, but you understand the problem? Yeah, yeah. So there is an input stream. There is a channel. The channel is noisy. Yeah, channel is noisy, but the channel's characteristics are known. Yeah. Now, what sort of a budget should you demand from your advisor in order to be able to communicate the results of your experiment to your collaborator? Yeah. So that the probability of error is kept as low as possible. Yeah. It's kept low. So let us try to understand what the limits of this problem would be. Yeah. So suppose they decide to use the channel n times. So Alice and Bob are sitting and trying to think about a code. Yeah. If you see 0000, please send me this. If you see 0110, please send me something else. So they go and design a code. So here, there are all possible sequences of the first of them, the last of them, and corresponding to each of them, there is this code word. Yeah. So the understanding is, if you see all zeros, put this into the channel. Okay. If you see all ones, put this into the channel. So these are elements of. So yeah, so we take the input alphabet to be 0, 1. So the number of code words here, number of rows in this table will always be 2 to the power Rn. And this may not be 0, 1. In general, this will be this is the input alphabet of the channel. So you take a string of length Rn and convert it into a string that the channel is willing to accept. But channel talks in this language of this alphabet, so you make it N. And you are asking, again, the same question, per use of the channel, how many bits of information can we transmit? Okay, sorry. Now, let us look at these code words and ask what their type is, or what is their empirical distribution of symbols. Okay. So this particular code word looks like, you know, each of these code words is a sequence of symbols from this alphabet. Yeah? And this alphabet has K symbols, K, as before. Yeah. Now, how many times could A appear, the symbol little a? So this quantity what are the possible values for NAX bar? What sort of values could it take? It could be 0, because if A doesn't appear in this at all, 1 up to it could be that all of them are A. Yeah. So this number is always in the range 0 to n. Yeah. So if I look at the empirical distribution, each letter not quite an exponential number in n. This looks like 2 to the power. Yeah, this number is not n. It's going like log n here. Okay. So this is a lower order sort of a number. So we actually can assume, so among these, we ask for the most popular type. Okay. So look at these code words and ask each code word what type you are, and there will be a large set, yeah, the total divided by this number, 2 to the power Rn divided by this. And this number hardly disturbs your Rn because there is an n here and there is only a log n here. Okay. So the net result of this is we might as well assume that they are using code words with the same empirical distribution. Okay. So if this was not clear, I'll let you think about it separately. Let us now assume that all our code words have the same empirical distribution. Let me just write it down. Yeah, we may assume all code words so each of these code words here has the same number of A's, same number of, sorry, what I meant by that, if this code word had 5 A's, this code word also has 5 A's. All the code words have 5 A's, but the A's can be in different positions. They have the same number of B's, but they are in different positions. Okay, so we can assume that it is because of this reasoning, not so important for us at the moment. Okay, good. Now, let us just, so we have a channel and we have fed in a sequence. So this is the channel. And here is the sequence, which is this Y1, Y2, Yn. Yeah. So, and its empirical distribution is P. Empirical distribution is P, and we have fed it into the channel. And I don't know why I wrote Y, X, these are X's. Yeah. So we have fed this symbol. We are just looking at one of the code words. One of the code words, we fed it here. What is going to happen? Are we going to get a deterministic output? No. When you feed something like this, if this was A, You fed A into the channel, some other symbol might show up. Then this was A again. It's not even clear that it's going to be the same because this time the channel does its own thing. Yeah. So various things will appear here. It will turn out that most of the probability here will be concentrated on a certain number of sequences. Sorry. So this part, yeah, is x to the power n, and this part is y to the power n. And when you feed a particular x to the power n into the channel, various y to the power elements of y to the power n can appear. And I'm drawing it like this just so that we have some mental image of what it does. But what I'm interested in is the probabilities. Okay. Now, in this sequence, the number of A's, yeah, was PA times n. So look at only those coordinates. Sorry, you must ask me because I sense that I'm not being very clear at the moment. So here is your x bar. There are some positions where A appears. So A appears in these positions. And how many positions are there? PA times A. Yeah. Now, when you feed A into the channel, the output comes according to what distribution? What should I write here? A, yeah? So when you feed this A into the channel picks an element Y according to this distribution and puts it here. When you feed this A, it again picks one of the Y's according to this distribution and independently puts here, okay? So let us focus only on the coordinates where A appears, yeah? Then what we expect to see on the output side, yeah, on the output side in the received word, in those coordinates is something that is typical according to this distribution. Focus only on those coordinates. The other coordinates we'll discuss later, yeah? So what we see here in these coordinates will be various symbols, but they are all being chosen independently according to this distribution. Yeah. Now, similarly, there are positions where the letter A prime appears. And if we focus on those coordinates, what we will see are independent draws coming from, yeah. And how many A's are there here? And how many A primes? The same quantity where I should write A prime here. Yeah, I'm not writing everything down, but you understand. So I'm trying to understand what these sequences here are going to look like. Okay. Now, most of the probability is going to be sitting on typical sequences. Yeah. And what will the probability of a typical sequence look like? We have, I'm going to write this down. Yeah. So probability. Typical sequences meaning if you look at the coordinates corresponding to A, it should look like it was drawn according to this distribution. When you look at the coordinates corresponding to A prime, they should look like it has come. For every such choice of little a, this fact should be true. Then we say that this is jointly typical with respect to this. Okay, yeah. But what will be the probability of any one such sequence? Well, the coordinates where you have A, we agreed. I mean, we had written it somewhere here, would look like 2 to the power minus n times h of remember the probability of any typical sequence look like 2 to the power n times the entropy. But now, I'll correct this. Yeah. So first of all, how many places have A's in them? So the n of the old calculation has now become PA times n. And the distribution which used to be P has now become Py given A. That means the entropy that I should write here is y sub A was this y sub A. Yeah, that is you have fixed x to be the value A, and then you are asking what is the conditional distribution. Yeah. That is about the coordinates where you have A. The coordinates where you have A prime, very good, times 2 to the power minus P A prime N H yes. And if I had to write this compactly, what would I write? I'm taking the average, there is an N, and I'm taking the average of these entropies weighted by the probability of PA. Do you see this anywhere on the board? Where was it? I erased it. This one. So this is okay. So basically, whenever you put its whenever you feed a code word into the channel, it sprays its probability. It sprays its probability onto sequences which each have this sort of probability. So the number of sequences, the neighborhood of this, the essential neighborhood, in where most of the probability resides will be, yeah, so the neighborhood two to the power n times h of. Yeah. So actually, the whole thing becomes a problem in graph theory. Okay, so let me go further. This is one of your code words, and it has its probability spread out over a neighborhood whose size is 2 to the power n times h of y given x. What does y given x mean? X had a certain distribution P, and then we know the conditional distribution of y given x. Yeah, so that is how you define y. Yeah, okay. This code word also has a neighborhood of size 2 to the power n times h of y given x. Why? Because one code word and another code word, the calculations are going to be the same, because this calculation just depended on how many A's are there, how many A primes are there, etc. The number of A's and number of A primes, etc. for this code word and this code word are the same. Okay, so everybody sprays their probability into this space, but equally into a large range. Yeah. Now, if Alice is transmitting this and or this and or let's say this code word and this code word, and suppose the neighborhood clashed and Bob received this word, he would not know whether it came from here or it came from there. Okay. So that puts a restriction on how many words you can choose here. Yeah. So if everybody has a neighborhood of a certain size, let's say L, and the total city has a volume of K. Yeah. The city has a volume of K, and everybody has a neighborhood of size L. What is the number of elements you can pack here so that their neighborhoods don't interact much? K by L? Yeah. Okay, very good. So yeah, so the number of code words possible. Yeah, approximately. A little bit of overlap is allowed, but those are technical details. Yeah. Now, the question is, I talked about a city here. What is our city? Yeah. See, all these sequences, their x's come according to the distribution P. I wrote P somewhere, but P. And then, whenever there is an A, what is generated here comes from the distribution, conditional distribution. So if I ignore this and look at this string alone and ask what are the distributions of various symbols, you will see that the empirical distribution of this is like the distribution of Y. Okay? So this space, these are all typical sequences with respect to the distribution of Y. How many typical sequences are there whose empirical distribution looks like Y? 2 to the power n times h of Y. So this city has only these many elements. And each of these code words is capturing these many elements. So the number of code words possible is 2 to the power h of Y. Oh. Yeah, h of Y minus h of Y given x. Let me not be cute. Yeah. Yeah, h of Y minus h of Y given x. What was the name for this? What is h of Y minus h of Y given x? It's the same as this. And this had a name. Yeah. So somehow, so what, as an engineer, yeah, sorry, what's the time? I'm over time. Okay. So let me just define the capacity of a channel and stop for the day, and then we will come back tomorrow. So to get the best out of the channel, what do the engineers do? They try to find the best empirical distribution here so that this mutual information is as high as possible. Okay, so the only design parameter that they have with us is what the composition of these code words should be. Yeah, what should be the composition of these code words? And you maximize over that. Once you have told me what X is, and you have already told me what the conditional distribution is, because that is determined by the channel, then the random variables X and Y, their joint distribution is determined. The distribution of X is determined by Y, by P, and the conditional distribution is already given by the channel. So we know the joint distribution of X and Y. For that joint distribution, there is some mutual information. And we try to choose the empirical distribution so that this is as high as possible. Did I write min or max? Yeah. And this is called the capacity. Okay. And the theorem that we will write next time is that if rate is less than capacity, then the probability of error goes to 0. And if your rate is greater than capacity, probability of error goes to. So if you want to ask for a budget, yeah, how many uses of the channel should I be allowed to per experiment? The answer is capacity of the channel. Okay. Yeah. Sorry, it was all over the place. But you got a sense of how mutual information arises in the area of transmission of information over a noisy channel. Okay. So next time we will try to determine the capacities for these two channels. Okay. And then I will do some. So like this was classical meaning. Yeah. Ancient. Information theory, there were two fundamental theorems about source compression and transmission over a noisy channel. We have sort of seen both of them. But it turns out that the notion of entropy itself can be used to understand combinatorial problems, and we will see some examples tomorrow. Okay. All right. So I can stop here. I'll take your question.